Okay, so once again, the idea that the homework is about is proving the existence of a fast stable manifold, and that turns out to be unique. So the construct that we did for the classic stable manifold will apply. Fast stable manifold is tangent to the span of the eigenvectors corresponding to the faster part of an otherwise stable spectrum, something like this. It's already unique in the linear system. I think I noted if something is already not unique in terms of the properties that you want to define it through, if it's already non-unique in the linear system, you will have no chance that it's unique in the nonlinear system, because you can always view the linear system as a special case of a nonlinear system, right? And if it really doesn't assume anything about the nonlinearities, which these theorems don't, then that result should already apply to the linear system. And we see that this is the only manifold that's tangent to this incoming direction, whereas when you take the weaker stable manifold, stable subspace, then there's infinitely many manifolds tangent to that, including the subspace itself. So already no uniqueness in the linear system. I noted for you that you have to change the norm in which you work, or the metric in which you work, to a weighted metric, and that's part of the homework assignment, okay? I did say, and just to motivate, that if we really want to use these results for something, then one of the most contemporary uses of this would be model reduction, because these days models tend to be incredibly more complicated. I just read somewhere in an article that given that the computational capabilities everywhere are improving, and given that all the simplest problems have already been solved, people are naturally drawn towards complicated models. That's really a new paradigm. I mean, I still remember, going to, when I was undergraduate, then the mantra that I heard that, no, you have to understand the simplest part of the system. The simpler your model is, the better, because you just want qualitative. You don't want quantitative. Science has grown a whole lot more ambitious than that. People now want to design a whole airplane without ever flying or doing experiments, right? In that case, you cannot, model it with an inverted pendulum or something like that, right? A fighter jet, although both are unstable, that's no question. But you have to be more specific. So these models are incredibly complex, and the computational capabilities have grown up. So that also brings in the idea that, of course, all right, but these are intractable, these huge models, right? And maybe we want to run them for lots of cases and want to test various parameters. So how could we reduce the computations? That's why model reduction is a really hot subject these days. Just Google it. There are conferences, focus issues, books, whatever. And in that spirit, I mean, the more important manifold, if there is one, is somewhere here, except that it's hard for me to point at it, because all I see from these trajectories is really just sort of an envelope, right? Why? Because at any point, if I draw a line, maybe it just becomes one of these trajectories at this point, and there will be another one continuing there, right? At what point do I give in and curl? Actually, it turns out there's really no way to distinguish in general these just by sight, because they all do the same thing. So that non-uniqueness, inherent non-uniqueness, comes, I don't know what this is doing. I got kicked out. So maybe it did an update against my wishes. Except that I don't know where I am now. So excuse me. So I had this, but that's not what I want to talk about. Online lectures. I think this is where I was. Sorry about that. So where was I? Already in the linear system, as I noted, you had this amount of non-uniqueness, and that's just inherited by the nonlinear system. Yet people badly want to talk about this here, if there is something like that. Informally, any object is called a slow manifold, even though I mentioned that the only case that we've so far in which that can be rigorously established is the singular perturbation setting, right? Nevertheless, people use this term. And I want to talk about this for the rest of the class, because I think it's just so topical and so important. It certainly entertains a large part of my own research group, my interest. So this falls in the category, this next one is spectral submanifolds and model reduction or reduced order modeling. These are the key words. And the type of presentation that I will follow, or nomenclature, is a paper that I wrote with Stan Poncio and a PhD student of mine just 4 or 5 years ago. And that the idea was to inject this idea into nonlinear dynamics, apply nonlinear dynamics from more abstract parts of the literature where it did exist, but in papers that don't have a single differential equation on it, but they're about mappings on Banach spaces. So it took us a while to realize that they're applicable to this setting and translate them in a way that people can actually hopefully read it and understand and apply it. And that has already been happening. So there's already now software and all that does that. So I'd like to just introduce you to the basics of that. And it's all about this, about model reduction. So a typical model reduction, and there are courses being taught about that as we speak, most likely even here at ETH, or books. But what will mostly be taught in these courses is projection-based methods. So the idea is that you have a nonlinear system like this one. It's fully nonlinear, and people do some analysis at an equilibrium point, identify subspaces that are spanned by eigenvectors of the linearization, and then take the nonlinear dynamics and project them down to these, right? And then they hope that that will be a good reduced order model. And clearly there are success stories that show that, yes, in some cases it does, right? So some of these projection-based models or methods that, again, this will be what you're seeing here probably would be a full course someplace else, and righteously so. One of them is called the proper orthogonal decomposition, which actually does not use the eigenspaces or eigenvectors of the linear operator, but tries to find combinations of those that are energetically dominant. So the idea is that construct linear subspaces for the linear part that are not distinguished necessarily by their geometry, but they carry most of the energy. So for instance, construct linear modes, combinations of the eigenmodes that would already capture, say, 80 or 90% of the energy of the linearized system, and then use those and project down to those. But ultimately, you're just doing a linear projection down to those. Another one is a very popular one, a dynamic mode decomposition, which actually, although I wrote it here, it's a bit different in nature. What it actually does, it works on data. And you have columns of observations next to each other, and you try to find a linear mapping that, when you iterate that mapping, that maps these columns of observations into each other, and you try to find the best fit. And there's an exact solution to that. So ultimately, that's actually not giving you a nonlinear reduced order model. So in fact, the fact that I wrote it here is not necessarily well justified, but it's a linear technique nevertheless. Galerkian projection is the good old method that people have been using in modeling. Basically, you have some PDE, you discretize it, you will have eigenmodes, and you take any number of them and you project down to them. So that's just really good old projection onto those without any fancy attempt to make those energetically dominant and so on. So basically, there are books, conferences, papers, whatever, written on projection-based model reduction methods. And in many cases, the only question when people talk about this is really not that whether this is right or wrong. They say, of course it's right. Why wouldn't it be right? If it's not working well, I just add more modes. And hey, at some point, I reach the full phase space when I have all the modes, right? Because when I project to my full set of basis functions, then I'm just back to the original equation of motion. So that's clearly correct. So maybe I can stop somewhere halfway. Instead of having a 500,000 dimensional finite element model, I go up to 250,000, but I'm still projecting down to a subspace. And the only question is then how do you select the modes and where do you stop? How many to include? And there are books essentially written about that, the choice of those modes. Okay, so let's just look at that philosophy, how that holds up in a very simple example, right? And that simple example is a two-dimensional ODE that I'm showing here, X and Y. It's nonlinear. You could say the first one is is strongly nonlinear, that people would say sometimes when the linear part is actually missing. The coefficient of that is 0 or near 0, so I neglected it in the modeling. Now this xn system in x and y is two-dimensional, and it has a fixed point at the origin. You plug in x equals 0, y equals 0, then that's clearly a solution. And if you linearize there, you don't have to work too hard. You see that already. The Jacobian matrix of the, when you calculate that, will only have 0 derivatives in its first row, and its second row, it will have a -1. So we're looking at a Jacobian like this when you linearize. Therefore, you can read off the eigenvalues immediately. One of them is 0, the other one is -1. So the linearization in xy coordinates looks like this, that this is what we would call a center subspace, right? And this is what we would call a stable subspace. Now, the usual argument that people have in model projection-based model reduction is that, okay, so that's really nice. So these are, they happen to be 0 here, but generally speaking, they might not be 0, but slowly varying. And therefore, these other modes will quickly die out. So I can understand the heart of the dynamics just by keeping the modes that are not varying at all, or very, very slowly. Mind you, this is not the exact full nonlinear dynamics. So we actually not have, we will have motion in this direction. But if the linearization tells us that the motion is frozen, then the nonlinear terms will introduce some slower motion near the origin. So let's just project it down. How do you proceed? So in this example, the projection is very easy to do, because normally if I had such an eigenspace geometry, then the projection would be like this. So it would not be orthogonal projection necessarily, but it would be parallel to the stable subspace. Maybe some would actually even then project orthogonally, but you see that's not necessarily a good idea. But here, it doesn't really matter. The two are already orthogonal. So the projection is nothing else, just setting y equals 0, right, in the equations. So that projects whatever vector I have here, whatever I have here for the right-hand side, it just projects it down to the y equals 0 axis. It's very hard to execute, right? And since this mode is just a graph over the x variables, I just have to pay attention to this equation, and I set y equal to 0 there. So this term is out. So the projected model is this. That's it. I cannot go with this idea, I cannot go to any higher orders. I cannot select any more modes either, because I'm done. This is the highest number of non-trivial mode selection that I can make. If I select one more mode, that's already the full system. So I'm not gaining anything else, right? So in terms of modal reduction, one rarely goes this high as I have just gone, because this is a codimension 1 set of modes, almost the full set of modes. So this will be the reduced order model. What does the reduced order model tell me about the system? The reduced dynamics is fully nonlinear. We've done this before. I mean, it's just a one-dimensional system. Remember, you plot the right-hand side as over the x variable, and wherever it's positive, wherever it's negative, you can immediately infer that here the right-hand side is the solutions are growing, and here they are decaying. So here you go. This is the full phase portrait of the reduced dynamics. You have a fixed point here at 0, right? This is a fixed point. So you have a fixed point there at 0, and you grow in this direction, you decay in that direction. It's a beautifully simple, very appealing reduced order model. And this is what the modal projection gives you in this case. And it better be correct. If it's not correct, I'm not sure what to do with this method, because there's no way that I can refine this further. Right? But for all I know, and you need to understand, this is what all you would know when you have a very large model. You will not be able to verify this. You just go procedurally and you say, you know what, I've done my best because I've selected the largest possible set of eigenmodes to which I can project, and it's still lower dimensional than the full. I can't go any higher, right? So this is as good as this approach gets. So an alternative would be, what I would like to do alternatively in this problem, and we already know how to do that because we learned that in nonlinear dynamics 1, is reduction to an invariant manifold. We know that the center subspace will give rise to a center manifold. We've learned that. We also know that in the other direction, you will have a stable manifold. So all the solutions will be driven to the center manifold. So it does act like a slow manifold. Center manifolds are generally not unique, but it plays the perfect role of a slow manifold, okay? And up to its own level of smoothness, it will have a unique Taylor expansion. There will be many manifolds here that come in, but you know, up to order CR, which is any finite R, they will all have the same Taylor expansion at finite orders. They will not be analytic Taylor expansions, so they don't converge to a unique center manifold. There will be a bunch of them. Anyway, we had a procedure for that, so let's do that. So we have a center manifold. It's non-unique, but CR. And this is the general phase portrait that I have shown. Now, I actually was a bit overly zealous here when I showed this solutions coming in. Who knows? I mean, that already assumes that along the center manifold, I have stability. I don't know that yet. In fact, this model tells me that I have instability, and in which case, when you come in, you would go like this along the center manifold. So here's the center manifold, the slower direction, you come in, no. Here's the center manifold if this reduced order model is correct. When you come in, then you go out. So it would be a slow, unstable manifold of a saddle point. But for that, we have a well-defined procedure. We don't have to guess. We don't have to project. This is exact. So we look for a center manifold that's a graph over that subspace. So that means that it starts at least with quadratic terms. A is x squared bx cubed cx to the fourth, right? So y equals h of x is the graph of that manifold that I'm looking for. And it might not hurt to refresh. Then how do you compute a center manifold? Well, you use the invariance of WC. That's the knowledge that we have from nonlinear dynamics, that there is an invariant manifold like that, which is a graph and has a quadratic tangency. And it is invariant, meaning that it's not just true at isolated points, it's true along trajectories. Therefore, I can think of this as y of t. I can think of this as h of x of t, because it's true along full trajectories. So why don't I differentiate with respect to time? So that gives me y dot equals, by the chain rule, this is h prime times x dot, okay? And y dot, I'm sorry, the y dot I will express in some other way. H prime from here is this expression, 2ax plus order x squared, right? Well, I just took the x derivative here. And then for x dot, that's a usual procedure to exploit invariance. I go back to the equation and I plug in x dot, and wherever I see y, I will plug in my h of x, because on W, on the center manifold, that's the case. So that's in the first round, and then whenever I see y, I plug that in. In particular, x times y will be ax cubed plus bx to the fourth, and so on, and I only keep the leading order term. So ax cubed, plus I had an x cubed here anyway, so I'm adding that. And everything else that comes from that me substituting here, the center manifold expression, this one, it's giving me higher order terms. So I only refer to them as order x to the fourth. Similarly here, I hope to get away for a leading order calculation. I'm not writing out more than just a leading order term. So at leading order, when I do this multiplication, I get 2a times a plus 1 times x to the fourth, because, well, I can just write this as a plus 1 times x cubed, and that needs to be multiplied by 2ax, right? So that's what gives me that, plus everything else is higher in order. So when we work with invariance, we exploit our ability to be able to write this in two different ways. The other way is that I go to the equation here, and I have an expression for y dot, but I use what it should be on the manifold itself. So I plug in, when I see y, the expression for the center manifold. So that's what I'm doing here. I take the equation, restrict it to the center manifold. So that means here's the right-hand side of the equation. I need to restrict it to the center manifold. So I plug in the WC expression. Remember, that was here. I've done that. And then I have the minus 2x squared, which I write there. So again, I collect all the leading order terms, probably did more work than necessary. No, actually, I didn't, because I surely need to have the x to the fourth term here, but it just so happens that I also have low order terms here. Here I go also up to order 5. So when you equate these two, which you have to, they have to be equal on this manifold, then you immediately get that, hey, this coefficient has to be 0 because there's no such term in the other expression for y dot. There's no quadratic term. So the only way these two can be equal is that this coefficient has to be 0. Likewise, b has to be 0 because there's no cubic term here. So a plus 2 is 0, therefore a is minus 2. And b minus b is 0, therefore b is 0. And then what remains is that now I have an expression for a. I plug that in here. And that coefficient must be equal to this coefficient. So minus c must be equal to 2a plus 1. And I plug in what I already have for a. So c is minus 4. So we did these types of calculations in the first semester. So WC, the center manifold, which is this graph, up to leading order, as I have just obtained, is minus 2x squared, because this is what matters at leading order. C, I've also obtained an expression for, and it's good to have it, but this term is out. I'm hoping to get away with the leading order approximation, at least to get an idea. And at the origin, it certainly the leading order approximation should help. So the reduced dynamics is now, there's no projection involved, but I go to the x equation, which is here, and I restrict it to the invariant manifold because the invariant manifold is going to be a graph over x. Therefore, it's enough to understand how the x evolution of the particle of the trajectory takes place, because the y is always enslaved to that. And very important to appreciate that we're not projecting to this plane, we are restricting to this surface. But since the surface is a graph over this plane, the dynamics on that surface can be solely described in terms of x. But we're not projecting to this plane. And in particular, we're not dropping this term. In our approximation, y is not 0. Okay? So the result of that, when I restrict to the manifold, so I take the equation, take its right-hand side, and restrict to the center manifold, which just means that for y, I plug in whatever I obtained here. I obtain x times, and now I'm plugging in y, right? Plus x to the cube. So if I collect, the leading order term will be this one, minus 2x cubed plus x cubed. Perhaps this is not entirely clear here. X cubed, right? So when I combine those two, minus 2 plus 1 is minus x cubed plus order x to the fourth. The advantage of this, that this is exact. This is supported by the fundamental theorems that we have: stable, unstable, and center manifolds. This is no guesswork. This is not a principle. This is a fact. And the very interesting conclusion arises from this absolutely correct tool of analysis, that the dynamics on the center manifold is in fact stable. Because if you play again this game, you're plotting the negative x cubed, right? Then it's positive here, it's negative here. So if this is the x-axis, right, then you have the fixed point here. It grows on the left-hand side because of the positive side, and decays on the right-hand side because of the negative side. So this dynamics is stable asymptotically at that, plus higher order terms. So the local phase portrait suggested by this is in fact the one that I sort of guessed at the beginning, is this. And one could say that, look, I have to be careful with this part because this is just a low order approximation, but it's always higher in order than this one, so it will not change the stability of the origin, because this dominates infinitely stronger, this term, anything that comes next to it when you get arbitrarily close to the origin. So this conclusion I can safely arrive at. And now you see an issue, because this is what the projection method gave us. The projection method gave us the opposite conclusion, that it's unstable and it grows unbounded. And that's not even my problem with this, because when you apply an approximate procedure, we all understand it's approximate. As long as you have room to refine it, you can always say, why don't I just to be safe, I check what the next order approximation would give you. But there is no next order of approximation. In this case, I've taken the full number of modes that I can still consider to be reduced, because it's a two-dimensional space. I got one, so that is like a codimension one set of modes. I did full projection. I wasn't holding anything back. You cannot improve this result. You're stuck with that, and it's wrong. That's the problem. This result, you can still work on and improve it to be even more accurate as you move away from the origin. This has potential, okay? The other one doesn't. It's done, and it's wrong. The result is wrong, and this is correct. So that's what one has to keep in mind when one sees projection methods applied to whatever, hundreds of thousand dimensional systems in which the ground truth is not known, that this can happen, right? There's no guarantee, because it's an ad hoc method. Now, of course, people will only show you the success stories, and there are, I'm sure, classes of systems in which that works well, but there's no a priori guarantee that it will. So one could say that maybe this is not working well because I picked a degenerate example. And that's probably what I would say when somebody showed me for the first time, because, oh yeah, well, there was no decay here in this direction, right? Under linearization. That's very non-generic in a real life system, because all modes are damped and they are decaying. It's in a real life mechanical system, right? So maybe this mismatch between the projection result and the actual analytic result is due to that. So let's see that. Let's take a more realistic example, still low dimensional and still very simple, so I can do all the calculations. So let's assume that all modes decay. This is a modification of the previous example. The previous example was this, and all I'm doing is just adding a linear decay here to remove that singularity of the, or degeneracy, I should say, of the linear part. So all of a sudden I have this decay term here, and I made it more slowly decaying. So in this direction, it decays slowly, it decays fast. So again, our first inclination will be to do modal reduction. If one is into projection, then we would again project into this one. Again, very easy to do. This is the slowest decaying set of modes, if you will, the largest one. I take this equation and project it down to that one. So whenever I see y, I plug in y equals 0, and this is what I get. So this is now the reduced order model from modal projection. What it does, it shows a fixed point. Luckily, it now, hopefully correctly, shows that that fixed point is actually stable. And it says that there are two non-trivial fixed points, because you can solve this equation and you get x equals plus 1/2 and minus 1/2. So it's a very nice reduced order model. It gives you something non-trivial. Truly nonlinear dynamics. Only nonlinear systems can have isolated steady states, two different steady states. That's a very nonlinear feature. No linear system can do that. So then this is now really a truly nonlinear reduced order model. So does the full system indeed have these equilibria? If it does, then this was a fantastic projection that came at a very low price. So on the fixed points of the full system, look at the full system, this has to vanish. So certainly I will have y equals minus 2x squared when I try to look for fixed points. So when I take that and plug it into the first equation, then I get this expression. I've plugged in my y equals minus 2 squared here, right, into this expression. And I'm trying to solve that for 0. And if you write this out, after factorization, you get this equation, x times minus 1/4 minus x squared. It certainly has the 0 solution. We knew that. I can read off that the origin is in equilibrium, but there's no other solution. So it just so happens that in the simple system in which by hand I can find the equilibria, the answer is that no, unfortunately, this system doesn't have any non-trivial equilibria. But the reduced order model just told me with certainty that it does. And again, I cannot improve this. I cannot go for higher modes, and I cannot increase my order of approximation. This is it. This is the best I can do with this method. And yet it gives you the wrong answer. After a very compelling argument that, yeah, we just basically project down here, we should get it right? Of course, one could say that, well, don't be so ambitious. Just basically use this part of the model, right? That's correct. Yeah, but that much I can get from the linear dynamics already, right? That type of behavior. I don't need to go do any nonlinear analysis. The linearization exactly gives me that. Right? Let's look at this. This is the linear phase portrait, right? So this is a concern. However, at this point, the modal projection guy who's trained in classical dynamical systems would also say that, well, I mean, maybe I don't get the whole thing right. At least I get it right here. But you know what? What can you do with your classical dynamical systems training? Because for you, the whole plane is just a stable manifold, right? And what else can you do beyond that? So you can't even reduce your system using classical dynamical systems too. Then if you're a bit better informed, you say, oh, of course I can, because I just learned about this fast stable manifold in nonlinear dynamics too, right? And I can reduce to that. And then you show the picture, and then you would be laughed at, because the person will say, this is the one that you're talking about. I mean, that's completely irrelevant for reduced order models, because most trajectories, except for the ones that live in it, just run parallel to it. So their asymptotic behavior is not captured at all by this model, right? In fact, this model is incorrect in the sense that it incorrectly predicts this fast decay rate, whereas most trajectories might only see that initially, but for most of their lifetime, they see a completely different decay rate. So you're not even getting then this right, this prediction, right? And that's true, right? So how can we get around that, given that we have no result for the slow, no uniqueness, or even at this point existence for the slow stable manifold? This is no longer a center manifold situation, okay? So no classic results are available. And also when you try to, and it's not that you haven't read enough, but you already see the issues that even if there was such a result, there's serious non-uniqueness, right? So this is certainly one of those opportunities, the center already in the linear system, right? That you have one candidate here that does this, and then in the nonlinear system, that the y = 0 is no longer an invariant subspace, but in the linear system, this is one candidate, but I said several times, these are also other candidates for such manifolds, right? So based on this, in the linear system, we don't expect uniqueness in the nonlinear system. In fact, we have Hartman-Grobman theorem that applies here, which tells you that since this equilibrium point is hyperbolic, which it is, therefore it's locally topologically equivalent to its linearization, the nonlinear system. So that means that the nonlinear system is a continuous deformation of what you see here. So something like that. So there's no unique entity to which one should reduce the model. But that's not the only alarming sign here. The other one is smoothness. This looks like a perfectly smooth situation in the linear system. And in order for us to refine and models and do Taylor expansions and whatnot, we do need the ability to differentiate. But I may have said this in some other, I think when we were talking about normal hyperbolicity, that a node like this, a nodal distribution like this, has a hidden, quite serious sometimes, non-smoothness that we don't see immediately, even though the right-hand side of this differential equation, not only is it C infinity, but it's in fact analytic. So that smoothness issue is the following, that it's C infinity even analytic. If you solve the linear problem, which you can explicitly, I'm showing that for a general lambda 1 and lambda 2 so that we see the message. In this particular problem, lambda 1 and lambda 2 were -1/2, -1/4, and -1. But to see the general message about non-smoothness, I replaced the 1 with minus, what was that? Minus 1/4 with minus lambda 1, and this is minus lambda 2. I can solve this linear equation. It's e to the minus lambda 1t times the initial condition. I can solve the second equation too, e to the minus lambda 2 times the initial condition. And to mimic what I had before, I'm assuming that lambda 2 is larger than lambda 1, okay? So in order for me to get an idea of what the shape of these are, time is an inconvenience. So I eliminate time and I link these two to each other to get a curve y is a function of x. So I divide by xt by x naught, right? And then what do I need to do next? I raise it to the, that is e to the minus lambda 1t. So if I raise that to the 1 over lambda first power, then I just get e to the minus t. I can do the same with this equation to express e to the minus t. I divide y by y naught and raise it to the 1 over lambda 2 power. That also gives me e to the minus t. And the e to the minus t from here and there, I equate the two. So I get this relationship. So if I solve this equation to express y as a function of x, to see what kind of a function these are, then I get constant c naught that depends on x naught and y naught, right? Times x to the lambda 2 over lambda 1, right? That's the solution when, so if you don't believe that, just multiply over by y naught, this power of y naught, and then raise both sides to the lambda 2th power, right? This is how you will get this expression. So this looks like a perfectly normal function, except that it isn't, in the sense that when you start differentiating this function with respect to x, then generally speaking, you run out of derivatives at the origin quite soon. Suppose that lambda 2 minus lambda 1 is somewhere between 1 and 2. That means you can differentiate it once, and that's it, not even twice. So the degree of differentiability is this number. You have to take lambda 2 over lambda when you take its integer part. And by construction in this problem, it's less than equal to, this is larger than equal to 1 because that's how I pick the eigenvalues, but it doesn't even have to reach 2. So if it doesn't even, certainly, or it will be an integer. So if I want higher order refinements as I normally want, for the case of center manifolds, certainly that was an option. Here, I have some limited legroom for most of these guys, if not all of them, because they have a very finite order of differentiability. I can't do calculus on them, right? So that sounds very pessimistic. And this is the second issue with an envisioned theory for a slow manifold attached to the origin. There's one exception that I mentioned here to this argument, is that when lambda 2 and lambda 1 happens to be an integer, then you can differentiate this function infinitely many times, as many times as you want, right? So it's only when it's not an integer. So this argument is true when this is not a natural number. Otherwise, in fact, this function is C infinity or even analytic. However, that is, you can imagine that's a very non-generic situation. If you have the slightest problem in your parameters or inaccuracy in the system, then immediately that's not an integer, and immediately then you have a finite differentiability. Once again, when lambda 2 and lambda 1 is an integer, then this is just x to some integer power. That you can differentiate as many times as you want, and after a while, it will actually become identically 0. So it's even analytic because it has a finite Taylor expansion itself. But that is very non-generic, and under the slightest perturbation to your system parameters, that will go away. Also, it turns out to cause other problems. So even if lambda 1 and lambda 2 are accurate, when you try to construct a slow manifold in this problem, this will lead to what we call resonances. And then, so it will cause a problem someplace else. However, this is therefore, things are not looking good, but there's one bit of hope emerging here. Just look at the case, this C naught, it depends on Y naught and X naught. In fact, if I multiply by Y naught and then set my Y naught equal to 0, C naught is 0. That's also one of those curves. In fact, it's this one, which I have known all along. That one is analytic. That's infinitely many times differentiable, arbitrary many times, and it's analytic and there's no problem with that. All others are problematic, but this one is non-problematic. So there is a unique one that has very favorable properties for potential model reduction, but unfortunately, this one will not survive. It's very specific to the linear system. However, one can ask the question, maybe there will be an other, in the nonlinear system, there will be an other smoothest invariant manifold out of the infinitely many that I undoubtedly should expect. Maybe there will be a smoothest one, and maybe on that one I can do calculus, and maybe, just maybe, that's also unique, because in this case this was unique, and that would address this problem. So I could be looking for the smoothest invariant manifold. So with those preliminary thoughts, one can try to set out and set up the problem. And it turns out they're all usable results from operator theory that even on Banach spaces that make this possible. I'll just stop for a second. Are there any questions? If you excuse me, I just need to drink one. It's water. No questions? So let me then give you what this setting is. So this will be, the area is called, as I mentioned already, spectral submanifolds. And spectral submanifolds are nonlinear continuations, if they exist, and unique ones, of individual subspaces within stable or unstable manifolds. So things like this. The way they differ from everything you've seen in the class, except for the fast stable manifolds, is that in nonlinear dynamics 1, we would have said that this is the most we can get in terms of reduction, because this is the stable manifold of the fixed point. That's it. That's all we learned about stable manifold, unstable manifold, and center manifolds. We would have said, sorry, dynamical systems cannot offer you anything else. This is a two-dimensional object. We can't go below that. Now, just couple of lectures ago, you heard that, well, we can refine that a little bit for fast stable manifolds, and those are in fact unique, but they also told you that they're mostly irrelevant too. So we are now moving towards establishing some relevance for model reduction by looking at the slower decaying directions. So here's the setup for that. So again, these will be, if they exist, they will be called spectral submanifolds, and they don't necessarily have to emanate from the weakest subspaces. It turns out it can be any combination of these subspaces, but let's see how that works. So the differential equation is this. You have a linear part in n dimensions plus a nonlinear part. It's assumed to be autonomous at this point. The nonlinear part is, well, it's nonlinear, so it's at least quadratic, potentially higher in order. And I assume that it's R times continuously differentiable. And unlike in earlier problems where the differentiability assumption mostly was serving just to ensure that I have at least local existence and uniqueness of solutions, here that would be absolutely crucial. You've seen already that differentiability is an issue. In the linear system, there are candidates for these types of manifolds, but their differentiability is not favorable. In fact, it might be not higher than 1. So this will play a role. And R is generally speaking a natural number, including, this is just notation, infinity, which is normally not included in this set of natural numbers. And when I write A, I just mean analytic. So if we write CA, then it's analytic. So R in this case is more of a symbol rather than a number. It's either an integer, a non-negative integer, but I also allow infinity there, and I also allow the letter A, which this would mean arbitrary many times differentiable, and this would mean analytic, which means that it has a convergent Taylor expansion. This just means it has a formal Taylor expansion, doesn't necessarily converge. So the eigenvalues of A, I label as lambda1 to lambda capital N, and this capital N is less than or equal to N. Why is that the case? Well, it certainly cannot be more than N, because little n is the dimension of the space, right? And capital N is the number of distinct eigenvalues. There can be repeated eigenvalues, and therefore it's it's sometimes less than n. You can have a double root. Maybe if you just have all the eigenvalues are single except for one, then capital N would be one less than little n. The ordering is this, that the real part of lambda n will be labeled as such if its real part, the highest one, if its real part is the smallest one. So basically n increases in this direction, is not in this notation. And the next one is n minus 1, capital N that is, and the lambda 1, I call it lambda 1 because that's the closest to the imaginary axis, right? So that corresponds to the weakest decaying direction that I have in the problem. My spectrum is like this. So I'm looking at a stable fixed point, fundamentally, and this is the eigenvalue distribution. So x equals 0 is asymptotically stable, and we know that it has a local stable manifold, but that's just an open set, right? So because all directions are stable, so that there's no opportunity here to reduce the dimension of the model. Okay. Now, what are the eigenspaces for this dynamical system? The eigenspace is the jth eigenspace. That's just one of the linear subspaces that you get from the linearization. So the way you construct them is you look at the jth eigenvalue and you look at the total span of eigenvectors real in the real setting. I'm not passing to the complex space corresponding to lambda j. The way you get that is easy when you only have real eigenvalues corresponding to it. Then if this is a real eigenvalue, then you simply take all the corresponding real eigenvectors. Normally, if this is a single eigenvalue, not repeated, then you just have one real eigenvector corresponding to it. But if it's repeated, then you will have general. You may generally have more than that, right? So then you take all of them and you take their span. Now, if lambda j is complex, then the way you get the corresponding invariant subspace, such as this one, is you take the real parts of its corresponding complex eigenvectors, take them as vectors. So the real part is just a real vector. And then you take the imaginary part without the I of the eigenvectors. That's again a real vector. And you take the span of those two. And that will give you an invariant subspace. You will have no invariant direction in that, but you get an invariant subspace. So for instance, when you have this is a complex conjugate pair with a negative real part, then the corresponding invariant eigenspace is something like a two-dimensional eigenspace. I'm showing here the case when you have two eigenvalues, one of them is a complex conjugate pair, and I refer to only one of them, and the remaining one is a real one, right? So in this case, it's a three-dimensional system. The dimension of the first eigenspace corresponding to the slowest decaying lambda 1 and lambda 2, which are complex conjugates of each other, is two-dimensional. Again, this is the span of the real part of the corresponding complex eigenvector and the imaginary part of the corresponding complex eigenvector. You take the span of these, and you may have you surely will have a stable dynamics within them because we're on the left-hand side of the imaginary axis, and the remaining real eigenvalue, say this one here. So imagine a case like this, that you have these two and somebody here is decaying faster because it's more to the left. And since it's more to the left, we're labeling it as 2 because this was our labeling scheme. So each of these eigenspaces then invariant under the linearized dynamics, obviously not under the nonlinear dynamics, but this is just sort of the notation to build it up. It's a bit more general than the setting that we've been looking at here in these examples where the two eigenspaces were always real, corresponding to real eigenvalues, and we just had two of them. There's a more general setting here. So this is an eigenspace. Now, what's a spectral subspace? A spectral subspace would be just any direct sum of these eigenspaces. So take these eigenspaces and you can select an arbitrary number of them and take their linear span. So take that direct sum. Since they're individually invariant under the linearized flow, or under even A as a matrix, then their span will also be invariant. So any object like that is called a spectral subspace, because it's a subspace of the spectrum associated with the spectrum. So shorthand notation for that is that you take these are the eigenspaces, all of them, right? And you then take a subset of these, so J, K, and K goes from 1 to Q. I can't do a summation over J, because if I did a summation over J, then this would just simply mean the first Q eigenspaces. But this approach is more general than that. I can just cherry pick eigenspaces that I want. They don't have to be the first Q or the first P. Any set of them is okay. So here's a picture. So, this is maybe the spectrum, and maybe the E that I'm building as a spectral subspace is the span of the eigenvectors corresponding to these, and with the span of the eigenvectors corresponding to these, and maybe I have skipped some of them. So that's entirely possible. That's why I don't want to be progressing here as over J, but it's any set of indices, J, K varying from 1 to Q. So in the extreme case, it can be just this particular eigenspace or this one. In both cases, Q, the index that measures how many of these I have runs up to Q. But in one case, the JK, the J1 would refer to this, and the other case, the J1 would refer to this. And I can have the combination of the two as well, okay? So this is also invariant on the linearized dynamics, any combination, and this is a spectral subspace. Now, one thing to characterize a spectral subspace will be important. Each spectral subspace, which is a linear entity, I'm not using any part of the nonlinear system here. Each spectral subspace have what we call a spectral quotient. And the spectral quotient is simply an integer associated with that. It's defined as the sigma of E. And the sigma of E is the integer which is defined of the following number. It's a quotient whose integer I'm taking, hence the name spectral quotient. So you take the smallest real part outside your spectral subspace, and then you take the largest real part inside that spectral subspace, take their quotient and take the integer part. So what does that mean? So in terms of, suppose I've chosen E, the spectral subspace, which included the eigenspaces corresponding to these guys, right? And this is the one which I excluded. But it can be any combination of these. In this case, the smallest real part outside E would be the common real part of these two eigenvalues, right? Because there's nothing smallest in this particular setting. This is already outside E, but it's not the smallest real part. This is the smallest real part, common real part. So I would put that real number here. Then I look all over E, and I find the largest real part. So this is the slowest decay exponent that I will ever see inside my own subspace. Okay, so I take the slowest decay exponent inside E, and I take the fastest decay exponent outside. I take the integer part of that and take the sigma. Now you might ask, what's the meaning of this? The meaning of this is the following. If you did the same gain that I did here for this simple linear system, and you looked at the differentiability of its various trajectories and surfaces formed by those trajectories, then you would find that this is the bottleneck. The same types of elimination that I used here to solve, you try enslaving various variables over the other ones to assess that these types of surfaces, which I again have in my current setting, but they are more generalized, and some of these directions, you might have spiraling in some of these directions, but generally speaking, you will have these cup-looking surfaces, and you would like to assess their overall differentiability, then you will be looking at quotients like this. And what you see here will be the bottleneck. So in some directions, this is the lower, when you test all possible directions, this is the lowest order of differentiability. So your linear SSM candidates, these surfaces, overall will not be more differentiable than this. That's the meaning of this. But the smallest, highest, because I'm checking all. I don't just have two directions to check enslave one over the other, but are several. So in this problem, in which we first encountered this, the linear part was -1/4 and -1. And the subspace was y equals 0, so that the spectral subspace was just y equals 0. And the spectral quotient, by definition, is what? You need to look at the fastest decay outside this E. So the fastest decay outside the X eigenspace is coming from here. That's -1. Then you look at the slowest decay inside. Well, you only have one direction inside E. So that's the whatever decay you have there, that would be the slowest decay. You put it here. So -1 over -1/4, that's just 4, and the integer part is 4. So in this particular example that we looked at here, where was that? Wherever it was, the spectral quotient of this subspace, spectral subspace, which is also an eigenspace, is 4. And that was incidentally the order of differentiability that the most I can hope. So this is a measure, this gives you a measure of the most differentiability you may expect in the nonlinear system. Now there's one final term that is associated with spectral subspaces. This is still a linear number. Everything I've done so far is just based on the analysis of the linear system. And the one last thing that turns out to be an important property of such a spectral subspace is any possible resonance conditions or non-resonances that it satisfies in the following sense. So assume that the dimension of the subspace is P. So when I combined, all these eigenvectors that span my favorite eigenvalues, then it's ultimately a P-dimensional spectral subspace, okay? I just indicated again that this spectral subspace may not just be an individual eigenspace, but it may be the combination of, the two-dimensional complex eigenspace plus this one-dimensional plus another two-dimensional complex, two-dimensional. So in this particular example, this gives me 2, 2, 2, 1. So it's a 7-dimensional spectral subspace. So in this case, P would be 7. And these are the individual, it's the direct sum of these individual EJKs, EJ1, EJ2, and so on. So the one corresponding to EJ1 would be the two-dimensional corresponding to this. This would be EJ2. This would be EJ3. This is EJ4. So the number of entities I'm summing up is 4, but the total dimension is 7. So what turns out to be important is how the eigenvalues inside the spectral subspace relate in any possible resonant way to the eigenvalues outside. So I take a linear combination of all the eigenvalues that are inside the subspace. So those are lambda J1, lambda J2, and so on. These are either real or complex. And I take an integer linear combination of these with an integer vector that has components, coefficients M1, M2 up to MP. It's MP, right? Because that's the dimension of this. So this is, just think of this as a sum of P numbers. It's a subset of the total set of eigenvalues. The funny notation J to J, it's not overcomplication of a simple thing. I can't run an index over J because that would only just cover a very particular subset of eigenvalues because I ordered them. So this is now an arbitrary subset of eigenvalues, okay? And I've taken this linear combination, and my notation with that will be this inner product of this integer vector M with lambda, which is a general notation from an eigenvalue vector of eigenvalues. Lambda J1, sorry. It's the lambda J1 up to lambda JP. Those are the JP, the ones that are here. And the symbol here, there's a sub E, means that I'm only taking the eigenvalues that fall inside the spectral subspace.
Professor?
Yep.
Just a quick question. How do you pick these subspaces? You pick them with respect to the highest order of differentiability, or?
That's a good question. The result as I'm giving you is completely general, so it doesn't restrict you to any particular consideration. That could be what you're saying, highest order differentiability. Usually you pick the smallest ones, slowest ones. So usually you will look at the spectrum, which is like this, and you would say, you know what, my simplest reduced order model would correspond to something that contains this one pair of slowest decaying modes. So if I'm very ambitious and hopeful, I can get a two-dimensional reduced order model, even though the original one was 100,000 dimensional. So then I would pick E corresponding to this. If there are interactions that I expect with other modes or resonances, as I'll get to that in a second, then you start enlarging that set. So you enlarge usually in practice in this direction.
Okay.
The reason why I'm making it that more complicated than it looks, because surprisingly, you don't have to go that way. You might take this one and you might take that one, it can be any combination. But in practice, you're driven by this consideration that you would like to build a slow manifold, which is a good model. So you work your way towards the decaying real parts. Is that an answer?
Yes.
Yeah, okay, good. Thanks for the question. That was actually an important clarification. So we call this spectral subspace non-resonant, or at least have no external resonance. That's more. If the linear combinations that I'm taking here never hit an eigenvalue outside the spectral subspace. So in other words, I try my luck with all integers m on eigenvalues that are taken from the restriction of the spectrum of A to E. So I only take lambda jk's that I get from the spectrum, which comes from the restriction of A to this particular eigenspace. This is just a more formal way of writing what I said in words. But the lambda L that I want to hit is strictly not in there. So what I'm trying to do here is take a linear combination of the eigenvalues in E to try and hit an eigenvalue outside. And if I'm unable to hit that with this linear, with the integer combination, then we say that this spectral subspace is externally non-resonant. I may still have eigenvalues internally, but it turns out that for the nonlinear continuation of the spectral subspace, that doesn't matter. All it cares about whether it resonates with the outside. And then back to the question that we had here, which is a very good question. It may happen that if I would say, you know what, I'm very ambitious, I want a two-dimensional reduced order model. And it turns out that I cannot be that ambitious if my candidate two-dimensional E contains eigenvalues that have an external resonance with another pair of eigenvalues. For instance, when, how would I show that? If I multiply these by 2, so I would have a pair of eigenvalues somewhere here, those would be in resonance with these eigenvalues, if I'm not mistaken. So some sort of combination in this sense, then I cannot choose that, it turns out, because the math doesn't work out, the proof. But when I have to enlarge and take those resonant eigenvalues inside E and then recheck. So I cannot afford to have resonances. If I see a resonance with some other eigenvalues outside, I have to enlarge E and include those guys as well. The mechanical meaning of this is modal interactions. So basically, if I say, oh, I have a mode which is the slowest mode, I think that it will capture my asymptotic dynamics. Somebody tells me that I'm not so sure because this mode happens to be in resonance with another mode. So if all your dynamics is going to this mode, there will be a coupling, a possible energy transfer to the other mode, and that will be excited too. So I don't think you're getting away with a two-dimensional model. And that's the mechanical intuition, which turns out to be very nicely equivalent to the mathematical intuition. Indeed, resonance with an external eigenvalue forces you to include that corresponding modes in your reduced order model. And that's what we're fishing for here. So for now, I assume that I have chosen E in a way that no such resonance condition holds. And then my question is that with this setup, does the spectral subspace E have a unique or hopefully smoothest continuation? I would call it W naught, because that's what I was hoping for based on the little linear example, right? That in the little linear example that I had here, I had no such resonance, at least not, well, there's an integer relationship between these two, but it turns out not to matter. Well, I'm getting ahead of myself. Let's not talk about the resonance. It's just that the idea here is that the linear system, I did have a unique smoothest object. Can I guarantee something like that in the nonlinear system? I will have many of them that are tangent to this direction, but maybe I can find a unique smoothest one and take that as a basis for my reduced order model, because on that one, I can just go ahead and do Taylor expansion up to any order. So I can refine my model. And the answer turns out to be positive. And this is what we spelled out in this paper, but the heavy lifting was really done in this more functional analytic papers by Della Liavi and others, and we refer to that. This is a paper from 2016. I think it came out in Nonlinear Dynamics. And basically, here's the translation of those results to actual differential equations and actual not so abstract notation. I don't think there was a single differential equation in that paper. That it was not an easy read. And you know, that paper is from way before. I think it's from the, I don't want to exaggerate, but I think it's early 2000s maybe. So almost, if I'm not mistaken, almost roughly 20 years old. And it was only used in that particular circle of people. Fantastic result, by the way. So assume this is the theorem as we translated it, or actually not just translated, but applied it to this particular setting, because the original result is for general mappings on Banach spaces, you know, none of the notation that I have here. So assume that you've selected a spectral subspace E, and you hope to be able to continue that, and assume that there is no low order resonance. So the low order non-resonance conditions are satisfied in the following sense, that you have a non-resonance condition as I have spelled out here, but I only want that to be checked or to hold for m integers. I'm in trouble because this is, I'm not in trouble, it's just that my notation is not great. I need a measure of the magnitude of m, and I don't see that written out here. So m, the magnitude of m is simply m1 plus m2 plus, but I need to take their norm. So I have p of these, mi. So the strength of the resonance, so the magnitude of the resonance, will be the sum of the absolute values of these coefficients. And I want a non-resonance to hold for E. So the combination, linear integer linear combination of the eigenvalues within that subspace should not hit any external eigenvalue, but I only need to check that in this range for n vectors whose norm falls between 2 and the spectral quotient. The spectral quotient was, remember, this number, which characterized the differentiability of generic candidate manifolds from the linear system. That pops up here. So you only need to check the non-resonance condition up to that order. But surprisingly, if you have a very strong resonance, so m would be 1, 1, for instance. So you have two eigenvalues here, two real eigenvalues in 1, 1 resonance, that's okay. So 2 is allowed, the equality is allowed there, but you only need to check up to that point. Once again, the eigenvalues that you need to test here are taken from the spectral subspace. They're all taken from the spectral subspace. These are integers, And the eigenvalue you're trying to hit is strictly taken from the outside subspace. And as I mentioned here, this is M1, M2, MP. Okay. So what is the type of resonance that's allowed? In fact, well, it turns out when this is 2, this is the case when I would have 2 equally decaying directions. So this is basically a degenerate node in that sense that the linear system would have all straight lines. And that's allowed, interestingly. But it's not allowed when you have a resonance that involves these trajectories. You will have trajectories like that in the linear system, but then no resonance is allowed between the two, at least not up to this order. Okay, so this is allowed, but other lower 1 to 2 resonance, whatever, 1 to 3, well, depending on what this quotient is. The higher that quotient is, the more restrictive this condition is, because then it means that you have to check more and more conditions not being fulfilled. If this is a low number, then 3, and there will be very few m's that satisfy that, and you only need to check for those. Then here's the statement. If we call SSM, spectral submanifold, the smoothest manifold that is a nonlinear continuation of E in the sense that is tangent to it, one can ask, does such a smoothest manifold exist to begin with and unique? Because smoothest means there is a unique one which is smoother than everybody else. It's not clear that maybe there's infinitely many of the same smoothness, right? Or maybe there's 3 who are equally smoother than the rest. So the SSM definition has more in it than one might first think. It's not just simply a manifold that's tangent to my target slow subspace, but also it has to be the smoothest, smoother than the others, to mimic what I've seen in the linear system, where this guy was smoother than all the others, and it was unique at that. All the others had the same differentiability. Remember that? This is the general formula for all candidate manifolds, and all of them had the same degree of differentiability, and it was all finite away from resonances when these were not resonant. Only the choice C0 equals 0 gave you one that was infinitely smooth. Even then I promised that, even though that looks like a clear case when you have a resonance, because then that gives you lots of differentiability, that turns out to be a headache when you actually try to construct the manifold. That's why the non-resonance condition actually excludes those cases. So here's the result. When such a non-resonance condition holds up to the spectral quotient, then there exists actually a CR-SSM, which means it's as many times differentiable as the right-hand side of the system. So that was my assumption about the right-hand side of the system. And this SSM will be as many times differentiable as the right-hand side of the system. Tangent to E. So it will be tangent to that spectral subspace at x equals 0. And its dimension will be equal to the dimension of E. So it is like the stable manifold and the center manifold up to this point, that it's really a nonlinear continuation of that manifold, right? Except that at this point, it's already implicit, the uniqueness here. I didn't say there is a unique one, because when I say there exists an SSM that already contains a smoothness statement, right? But what's interesting about this, that this surviving WE naught, where's my notation? Yeah, it's associated with that particular spectral subspace, right? So it's already unique. Irrespective, this might be 100,000 or whatever, but it's already unique in this class of functions. So in other words, it's the spectral quotient plus 1. That's the class of surfaces in which this is the only one. Only this one reaches that level of smoothness. It might be much smoother than that. It might be, 100,000 times differentiable if the original system was. It will be analytic if the original system was analytic, because it's the same R at the right-hand side of the system, but it already prevails in a potentially much lower smoothness class. Everybody else, all these other guys here are they're following in smoothness the SSM up to C to the sigma E. But if I just add one more degree of differentiability, they're all lost. That many times they're not differentiable. So that's already a statement about them as well, that they are only differentiable up to C to the sigma E. But if I just take one step further in differentiability, they're all gone. And there will be one that uniquely prevails, which is great. That's the kind of thing we were looking for, because on that one, I can now do the type of model refinement that I always wanted to do, say on center manifolds. I can now go up to any order of differentiability that my right-hand side allows, the original right-hand side. So I can have a reduced order model on that one, which is as smooth as the original model. On these other guys, I couldn't. There would be a serious limitation there, right? So that's important to note about that. And then if F0, which is my original nonlinearity, is jointly CR in X and mu. And this is an important statement here, because first time ever, I'm also bringing in a parameter into the problem, right? All these practical problems have parameters in it. And if I don't have a parameter dependence, which I didn't list here, because I didn't want to complicate the setting, but now I'm assuming that in fact, I already had a parameter here. And I want robustness with respect to that parameter. And it turns out you do have robustness with respect to that parameter. Namely, if F0 is jointly CR in X and mu for some parameter vector mu equals RP, which just means that if you take the mixed partials of F0, these are the mixed partials, some of them are with respect to X, some of them are with respect to mu. You take J partials with respect to X, K partials with respect to mu, and J plus K is equal to R. So that's what it means for F0 to be jointly CR in X and mu, okay? So if after such a differentiation, you still get a C0 function for all choice of J and K, that's what I'm just spelling out what this means, okay? Then WE0 inherits that. In other words, it will have a good many derivatives with respect to the parameter as well. So you can also expand it with respect to parameters. It will be robust with respect to parameters. You can do approximations. You can explore its parameter dependency. So if F0 is C infinity or CA, then including mu, then you in fact will have a similar dependence on X and mu. So if this was analytic, if F was analytic or smooth with respect to the parameter as well, then so will be the manifold. So you will have smooth analytic persistence for this manifold, differentiable persistence up to any order. And then basically, if you want the details of this, then that's written out in this paper. Again, it's essentially a translation / application of very general results in infinite dimensional dynamical systems. So the end result is that high order Taylor expansions will capture uniquely this, because if you start expanding, you restrict the same way as you would to a center manifold, then for a while, these guys will have the exact same expansion as you would for all center manifolds. They all have the same restricted dynamics. But the difference between center manifolds and this subject area is that up to this order, all of them will have the same Taylor expansion and reduced dynamics, all of them identically. But you just step one more step, you lose all of them. And whatever Taylor expansion you continue doing will only be valid on this single one. But on that one, you can go up to any order. So you have an infinite opportunity to refine your model further, but you have lost these guys, which is a good thing because you get a uniqueness, right? You get uniqueness. So you can get any required accuracy that you want. And again, that's usually the issue when you have a projection-based method. You may have more modes to add other than the example in which I maxed out on the number of modes. but that's the only way you can refine your model. You increase its dimension. So if it doesn't work for 5 modes, you go for 6 modes. If it doesn't work for 10, you go for 12. If it doesn't work for 20, you go for 100 or whatever, increasing the size of the dimension. With these dynamical systems-based methods, which have guaranteed mathematical foundation and differentiability, you extend laterally. You don't increase the number of equations, but rather you increase the accuracy of the nonlinearity. So that doesn't increase the cost of running your reduced order model. It just refines it, and that's a big advantage. And there's a systematic way to refine that. Whereas with model projections, there's so much you can do. And once you have reached codimension 1, there's no further refinement, and that may well be wrong. I think I stop here and I'll take any questions you might have. And then tomorrow I'll just go back to this example that we looked at and see how this SSM, the spectral submanifold, comes into play in that problem. One thing is sure, I feel that if I don't write, then I surely talk more. So it might, I don't know if in the end it's faster or not, but it's more tiring because there's no off time, right? I keep talking. Okay. No questions? Okay, then let me then show you tomorrow how this works in action on these probably semi-abstract results, what they buy you in practice. See you tomorrow.